Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the previous lecture. In the previous lecture, we discussed an example. So let me write that. Our example was an assembly of particles with two states. Let me use another color here. Sometimes it is called sip-in half solid. So our assembly of particles with two states, which we discussed, also called sip-in half solid. Let me refresh your memory. Let me write first here, continued with previous lecture, continued with previous lecture. So idea was we considered an assembly of n localized weakly interacting particles in which there are just two states, two one particle states. We labeled these states as j is equal to 0 and j is equal to 1. Ground state j is equal to 0 had energy epsilon naught, and the state with labeled with j is equal to 1 has energy epsilon 1. So we had total number of n particles in this assembly, which we assumed localized and weakly interacting. Then we wanted to figure out the expressions for the properties of this assembly at some given temperature T. This was our purpose, to find out the expressions for different properties of this assembly at a particular temperature T. So in the last lecture, we first wrote the expressions for, or figured out the expressions for the distribution numbers. The distribution numbers also called the occupation numbers of the two states. So first we wrote down the expression for the partition function of this assembly. We wrote this expression. Let me use this color. So we wrote the expression for the partition function as z is equal to exponential of minus epsilon naught over kbt times 1 plus exponential of minus epsilon over kT. In the last lecture, we named this as equation 1. Z is the partition function, so it is exponential of minus epsilon naught over kT. Kb is the Boltzmann constant times 1 plus exponential minus epsilon over kBt, where epsilon, as you know, this epsilon is epsilon 1 minus epsilon naught. So it is the difference between the energy levels epsilon 1 and epsilon naught. Then we said that this first factor in this partition function, let me write this with another color. This first factor in the partition function, this thing, we named it z of naught, which is the 0 point term, and the second one, the second factor, we labeled as z of th. We called it the thermal term. As you know, this 0 point term depends only on the ground state energy epsilon naught, and the thermal factor in this partition function or thermal term depends only on the relative energy epsilon between the two levels, right? Then we found, using the Boltzmann distribution, we found the expression for the distribution numbers. Let me write those equations. We found that n naught, that is the distribution number pertaining to the ground state, is equal to n over 1 plus exponential of minus epsilon over kT, which we can write as n over z thermal. This was the expression for the distribution number pertaining to ground state. So it is n over 1 plus exponential of minus epsilon by kT, or you can write it as n by z thermal. So in the last lecture, we're continuing with that. We named this equation as 2a. Then similarly, we found the expression for n1. Let me write that expression in another color. The distribution number pertaining to the state 1, which we label as by j is equal to 1, this n1 is equal to n exponential of minus epsilon by kT over z thermal. Let me encircle it. We named it as 2b. This is 2b. So it is n1 equal to capital N times exponential of minus epsilon by kBt divided by Z thermal. So these were the expressions for the distribution numbers pertaining to the two states of the system. Then we plotted these distribution numbers with temperature, and we defined the characteristic temperature theta of the system. That characteristic temperature by definition is epsilon over Kb, right? So we will continue today with that lecture. So today we want to first figure out the expression for the internal energy of this system. So first we discuss the distribution numbers. Now we will discuss the internal energy U. So our second thermal property of this system which we want to discuss is internal energy U. Expression for internal energy you can simply write as N naught epsilon naught plus N1 epsilon 1. I name it equation 3. N naught is the occupation number of ground state, and epsilon naught is the energy pertaining to ground state, and N1 is the occupation number or distribution number for state J equal to 1 with energy epsilon 1. So this is the internal energy of the system, which can be adjusted or rewritten as, I can write it as N epsilon naught plus N1 epsilon. As you know, epsilon is the energy difference between the states, epsilon 1 minus epsilon naught, and N is the total number of particles in the system, that is N naught plus N1, right? So it can be written, you can check it. This is a little assignment. I will write it in different color. Let me use this color. Check it at home. So we can write the internal energy of this assembly or our system as N epsilon naught plus N1 epsilon, with N1 given by equation 2. Our N1, let me, where is my this? N1 is given by this expression, right? Or not? N1 is given by this one, 2b. This is Z. So N1 is given by equation 2b. Now the first term in this equation is the 0-point energy. So let me name it. This is the 0-point energy. That is the internal energy at T is equal to 0. And the second term is the thermal energy. It is thermal energy. You can call this term as U of 0. It is the internal energy of the system at T is equal to 0. And this thermal energy you can write U of TH, that is U thermal. And this U thermal depends on the energy level spacing epsilon and kBT only. This thermal depends on epsilon and kBT because it contains N1, and N1 from equation 2b depends on these two things, right? We can plot this with temperature. Let me plot it. Let me draw the figure. First, I will use some other color for it. Let me use green. So when we plot this internal energy with temperature, let me complete the figure first. On this side, it is internal energy. On this side, we have temperature. Then here I have 0. Let this be theta. Theta is the characteristic temperature. Here it is 2 theta. Then here it is 3 theta. Then let me label this graph on this side. Let me use another color now. I will use red. So this is my characteristic temperature. This is another line. Let me draw it. Then this is the maximum internal energy here. This has a value U of naught plus N epsilon by 2. I will explain how. I will use another color for the curve. So if it is the zero-point energy here, U of 0, then the curve will go like this. If we go like this, let me draw it clearly. Try more clear curve. Is like this. I think it is okay. Now see, let me name it figure 2. So this figure gives me the variation of internal energy with temperature for this sipping half solid, U of 0 is the 0 point energy. So you can see from this graph, even when T is 0, you have some internal energy in the system which is called 0 point energy. That is the first term in the expression, which is independent of the temperature. So this is the 0 point energy, and this thermal term changes with temperature. So you can see in this figure that there is a transition from low to high temperature behavior around the characteristic temperature theta. Here the temperature is characteristic temperature theta. The behavior has a transition. Now when there is small temperature compared to theta, you can see curve has one behavior. Then when T is large compared to characteristic temperature, this internal energy then saturates. It approaches the value U of naught plus N epsilon by 2. Why? Because you know from the last lecture, at high temperature, this N1 at high temperature compared to the characteristic temperature becomes capital N by 2. That's why you have here the maximum internal energy the system can attain is U naught plus N epsilon by 2. This is how the internal energy of the system behaves with temperature. So we have been able to discuss the variation of internal energy of the system with temperature using our ideas of statistical physics. Let us move now to another property, that is the heat capacity. So let me write the third property of this assembly which we want to discuss is the heat capacity. Specifically, we write the expression for heat capacity at constant volume. Heat capacity at constant volume. Remember the definition of heat capacity is the amount of heat required to raise the temperature of a body through unit degree Celsius when you are putting the heat in the system at constant volume. Then your heat capacity is heat capacity at constant volume. And heat capacity at constant volume means the heat capacity at constant energy levels, because fixing the volume of the system fixes the energy levels. Now, how we obtain that? We obtain that by differentiating the internal energy with respect to temperature at constant volume, or this constant energy levels. So my heat capacity at constant volume, I can easily obtain it. I have to differentiate my internal energy with respect to temperature, but my energy levels or volume is constant, right? So when I do that, I have the expression for internal energy, that is this. But in this expression 3, I have to replace N1 by the expression given by equation 2b. Then I will differentiate that internal energy with respect to temperature, treating the volume constant. When I do it, I will write directly the result. I will get this. CV